Hello and welcome back to AP Pre-Calculus. Today's lesson 2.6 is competing function and model validation. So here in AP Pre-Calculus, the main models that we normally deal with are our three: linear, quadratic, and exponential. That is because in the real world, we can model a lot of things after one of those three functions, okay? So on this AP exam, we are going to be dealing with linear functions, right? Or linear models in this case, because we're going to try and remember, a line of best fit, that kind of idea. And remember, a linear model, we have a constant rate of change, or the slope stays the same throughout the whole thing. All right. We'll do quadratics, where we'll make this U shape, or it might be an upside down U. Just depends on what the data looks like. And I want you to notice that we're not going through all of these points, right? This is a regression model. It's the best fit model. We're not going to hit all of the points, but we're trying to get as close as we can to all of them. Okay? And remember, our rate of change, if it's concave up or if it's a U going up, it'll always be increasing. If it was concave down, our slope would always be decreasing at a constant rate. Okay? Over here, they stay the same. On quadratic, they increase or decrease at a constant rate. So I keep going up 5, or I keep going down 2/3, something along those lines. And then last is our exponential model, right? We have a growth model given here, but it could be a decay model going the other direction. This is where concave up, our rate of change would be increasing proportionally, meaning we would be multiplying by the same thing over and over again. Okay, so those are our three models that we'll be working with today. All right, so let's try this out a couple times here. So I'm giving you a table of points, right? And I want you to go ahead and graph them. So I'm going to graph them on A, and let's look at it. All right, so there we have 5 points graphed. And if you look at that, that looks pretty linear, right? So if I could take a line and put it in there, it might look something like that. So we would call this a linear model. And again, notice that I didn't hit all of the points, but I got as close as I could to with an estimate linear model. Let's try B. Let's go ahead and graph those points. All right, as we look at that one, I mean, that looks like it goes up and comes back down, kind of makes a U-looking thing. So it might be a graph that looks like this. So it could be something that looks like that. And again, look at those points. Like, I'm not close to some of them, but I'm as close as I could probably make it. So this would be quadratic. Okay. Let's try it again on C. All right, there are my points graphed. I start high and I start shallowing out with a little bit of a curve. So this is probably going to be exponential. Like, let's see if I can draw a graph that kind of models it. And it could look something like that. And I will tell you that we don't have enough information to know for sure, because if this data keeps going out on the x-axis, we don't really know if it's going to start going up. But for what the data we have, we would say this is an exponential model. Okay, let's try D. All right, there's our points. And if I tried to fit something in there, it might look something like that with a little bit of a curve. So that's another exponential model. What's the difference between these two? So what's the difference between these two? Well, C is kind of decreasing, right? It's getting smaller. Concave up, actually. So my slope is increasing, but the value of my function is decreasing. So that would be what kind of model? That would be a decay model. So what do we know about a decay model? Our B has got to be in between 0 and 1. Where D is a growth model, what do we know about B? Has to be greater than 1. Okay? So remember, we are making approximations to a function. The data doesn't fit exactly the function that we're coming up with. It is an estimate of what we could use to predict things, right? So we know we're going to be wrong. So what we have is this thing called a residual, which means how wrong were we? Well, how off is our model compared to the actual data? So when we have that difference, when we're not right on the actual model function line, then we have this thing called the residual. And to do that, we would do the residual is equal to the actual output value minus the predicted. An easy way you can remember this is you are in an AP class. It's A minus P, actual minus predicted. If you get a positive value, that means your model underestimated what we got, right? Because you're above what the predicted model. So they underestimated. If we have a negative, it overestimated what we should have got because we got this number, they predicted bigger, and that would give us a negative value. All right, let's look at example 2. So here we have a table of values, and there are the weights of newborn babies. So we're going to make a function W of t in kilograms, where t is the number of months since birth, and W is obviously the weight. Okay, so we're going to go ahead and take our calculators, get them out. We got to make a couple of lists. In list 1, we want those t values. In list 2, we want those W of t values, x's and y's, right? And then go to calc, right? Down here to 8. We could use 4, but we want to remember to use 8. And then just run through all these. Make sure that we store the regression equation in y1. If you don't remember how to do that, you can do alpha trace, and it brings it up. And just choose y1. And then hit calculate, all right? So once you do that, we should get these numbers right here, okay? So are we getting that? So if we are, then we can write our equation as W of t equals 3.34 plus 0.8 t, okay? So that is our regression model. This is our estimation of the line of best fit. And they want to know what would be the weight of a baby that is 2.5 months old. So you could do the math. You could put the 2.5 in the t. It's not real hard. But since we stored that y1, we could just go ahead and hit alpha trace, hit y1, and then in parentheses, put 2.5, and it'll kick out 5.34. And we want to put kilograms with that, so there we go. Okay, so let's look at C. Here's where we get to our residual idea here, okay? So it says the actual weight was 5, so my A was 5.5. My P is 5.34. And remember, residual is equal to A minus P. We're in an AP class, okay? So when you subtract those two things, what do we get? We get 0.16 kilograms, right? Positive. So what does that mean? Our model predicted less than what we actually saw. So our model underestimated the true weight of a 2.5-month-old baby. Okay? So we have this thing called a residual plot, okay? And we can use it to check the appropriateness of a model. So when we have a residual plot, it's basically going to be a graph that looks like that, and this would be 0. So if I had all of my dots, like if I, remember I'm plotting the residuals, okay? So if the residual is on the line, the difference will be 0, right? So if they were all on this, then our model was basically exact, okay? That doesn't happen in the real world. Things get a little bit messy when we're dealing with real data and not, stuck in a classroom dealing with theoretical math. So we have to look at our residuals to see if maybe we should have used a different, or at least know that, the model that we used wasn't really a good predictor. So What we're looking for is there a clear pattern left over in the residual plot? If there is, then what we used was not appropriate. What does that mean, a pattern? Well, if it looks like something like this, that's a pattern, okay? And it could go the other way. So in AP Stats, we call it a frowny face, a smiley face, or a sideways Christmas tree. What does a sideways Christmas tree look like? Like if it looked like this. And it kind of came down to a fan. All right. So those are the three things that we look for in AP Stats: a frowny face, a smiley face, or a sideways Christmas tree left over in our residual. Don't look for other types of patterns. Just those three are the main ones that we worry about. All right, so here we have a residual plot. So this, we still have an x-axis. It's the same x-axis that we would have in our graph, okay? So, but the y-axis now is the actual residuals. How far away from the predicted line was I? So like this point right here is almost 2 above what they predicted. This point right here is a little bit more than 1 below what they predicted. So let's read the question. An exponential regression was used to model the data set. The residual plot for the exponential regression model is shown above. Which of the following is the best conclusion about the appropriateness of the exponential regression model based on the corresponding residual plot? So I'm going to look at this residual plot, and I'm looking for a frowny face, a smiley face, or a sideways Christmas tree. The main thing is we want to have, what I tell my kids in AP Stats is if you stuck your fingers into a paint bucket and then just splatted it against paper, like if you just flick your fingers, the dots would go all over the place. And that's really what we're looking for. We don't want to see a smiley face, a frowny face, or a sideways Christmas tree. And I don't see that here. So the exponential model is probably a good model to use because we don't see a pattern. Which one of these says that? I believe it's C. All right, here in example 4, we're trying to figure out which of these is the most appropriate model. So that word most kind of gets people, especially algebra teachers and really strong algebra students, because we are so used to it being exact. Like we live in a classroom and we teach it in a subject that is very much theoretical. And so we get used to being able to say equals a lot. Well, out in there in the real world, when you're dealing with data, data is not exact. It is not theoretical. It's real world. So things don't fit as nicely as we would like them to in the sterile confines of our classroom. So sometimes we have to choose something that's close. And I know that a lot of algebra teachers don't like that. Calc teachers don't like that. But that's just the way of the world. So I'm going to look at these 3 regression models. I have one made. It's all the same data. I ran it once with a linear regression model, once with a quadratic regression model, and once with an exponential. And I want to know which one of these is the best. So I'm looking at the first one, the linear regression. I see a clear smiley face pattern. So I am not choosing A. Well, it's not even an A, but I'm not choosing the linear regression model. The quadratic, it doesn't have the 3 that I talk about, but if we were to split the data right here, this side has a smiley face and this side has a frowny face. I know it's not a pattern for the whole model. So like if the exponential model was terrible, I might go back with the quadratic. But if you look at the exponential one, it just kind of scattered around. And that's really what we want to see. So on this one, we would choose the exponential model. When we get to the AP test, we got to make sure we're answering everything they wanted to. They did not just say which one is the best one. We have to give a reason for it. And we chose the exponential regression model because it did not have any clear pattern in the residual plot. So that's what we would write in our answer. All right, last example of this lesson. Mr. Passwater, the awesome teacher who shared all of these notes with all of us teachers out here in the AP Pre-Cal world, hopes to make it into the Guinness Book of World Records by painting the world's biggest mural on the sides of several downtown buildings. His mural will consist of many painted circles of various sizes, where each circle is painted a different color. He wants to create a model to determine how much paint is needed in quarts for a circle of radius in feet of arc. All right. Should Mr. Passwater use linear, quadratic, or exponential in this situation? And then explain your reasoning. Remember in an earlier lesson, we talked about how can we tell which one we should use. And we said something about area and something about volume. Okay. So area would be a quadratic idea. Volume would be a cubic idea. Exponential means it's going to grow and grow and grow without bounds. So which one might we use here? Well, we're going to fill in a circle. That's an area idea. So we would use a quadratic model because area used square units, and when we have squared, that's a quadratic. Okay? This is what we would write. And that would be enough to get you credit for that question. Let's look at B. After creating his model, Mr. Passwater uses it to purchase different special paint colors to use on his mural. In this situation, do you think it's more appropriate for the model to underestimate or overestimate the actual amount of paint needed? Give a reason for your answer. So we have to go a little bit beyond than just doing math. We actually have to think about this in real world context. How could overestimating or underestimating be a problem? If I underestimate the amount of paint that I need to use, I'm going to run out of paint, and my mural is going to look undone. That could be an issue. If I overestimate, I bought too much paint. I may have spent a little bit extra and have paint left over, and I didn't need to spend the extra money, but my mural is done. Which one is better? That's kind of what we have to figure out. So this is what I would have written for mine. You could have said it a little bit different. I don't think underestimate would have been a great answer because you don't have a finished mural and then it just looks weird, okay? And that completes today's lesson.